Okay, if you've watched some limit videos prior to this one on this website, and if you haven't, I would encourage you to. What you're starting to notice is that each video and each limit problem is basically going to be a certain type, right? And so far we probably had 3 or 4. In total we'll have 5 or 6 sort of tricks or types of problems. And your job as a calculus student is just, when you're given a problem, a limit problem, just to look at it and say, what problem does this remind me of, so I can figure out which of the many tricks I know I should apply to this particular one. You know, if it's x approaches infinity, we're going to want to get rid of everything except the biggest term. If it's a polynomial, maybe we'll want to factor it. And we just know some tricks, right? Well, today, in this video, we're going to look at the trick to use when there's a sine or cosine involved in a limit. And usually it's just when the limit is, it's a big fraction, right? Like you have a sine or cosine over something, or something over a cosine, that kind of thing. Just to warn you, if you're in AP Calculus, you're going to need to know the unit circle. Like throughout the year, there'll just be a few problems in each chapter that involve plugging in values from the unit circle, like having to find the cosine and sine of angles. So if you're not solid on that stuff, go to the trig chapter of this video, go to the trig class on this site, find the unit circle chapter, and just go down to the bottom. You don't have to do all the videos. Just go down to the last couple that are about tricks for memorizing the unit circle, and that'll really help you out. If you have an easier class, or like you're in calculus for business or something, usually they're really nice about either not making you know any of the unit circle at all, or they'll let you like bring in a note card that has some key values on it, whatever. So you're probably not in as much trouble as the AP students in having to memorize everything. All right, so first things first, whenever you see a sine or cosine in a limit, plugging in still works. It's a great idea, great way to start a problem. So right away, just plug in. Now again, you'd have to know the unit circle, but the sine of pi over 2 is 1. The cosine of negative pi over 6 is square root of 3 over 2. And the cosecant of pi, I'm not sure, but that's the same thing as 1 over sine x. And sine of that is 0, so this is 1 over 0. Is that indeterminate? Nah, it's just infinity or does not exist. So the limit does not exist because the cosecant does not exist. It's undefined. All right, so that is plugging in, and you got to know your unit circle to do that. The rest of the time, though, we're going to be looking at indeterminate situations. So, for example, forget it says 1 right there for a second, and forget this says 0. If someone just gave you this problem, limit as x approaches 0 of sine x over x, you're hosed, because if you know your unit circle at all, you know that sine x is 0, and 0 is obviously 0, so we got 0 over 0, which is indeterminate. But of course, any tricks we've seen in previous videos are not going to work here. There's no way to reduce this or whatever. It's not a polynomial. Similar thing happens here. Cosine of 0 is 1, so this is 1 minus 1, which is 0, over 0 again. So once again, we have 0 over 0. What can we do about it? Well, it turns out some helpful mathematician has gone in and figured out that the limit as x approaches 0 of sine x over x actually equals 1. So this is just like a theorem or a postulate you just need to take on faith and use as the basis in solving these problems. Similarly, they did the math on this 1 minus cosine x over x thing and discovered that its limit as x approaches 0 is 0. So the limit of the sine one is 1, the limit of the cosine one is 0. Good to know, right? So the question is, what kind of question could they ask you about these? Well, you'll notice, so let's look at this first problem. It looks an awful lot like this. It looks an awful lot like this sine-based one. What's the difference? Well, in the sine x one, the x's match, right? We've got an x in each one of them. Whereas in this one, we've got a y, and then we got a 3y. If we just had this part, just the sine y over y would be set. We just found out that equals 1, right? They just told us so right up here. But with that 3 in it, things get wacky. That 3 doesn't belong there. So what we're going to do is use our limit properties to bring that 3 outside. Because it turns out that having a 3 in the denominator is just like multiplying by 1/3. And we're just going to, because it's a constant, we just move it out front. So the limit of sine y over 3y is the same thing as 1/3 times the limit of sine y over y. And guess what? This puppy right here is exactly what we want. That's word for word, letter for letter, this thing right here. So we just know that this equals 1. And now that we've subbed in 1 for that, we just got 1/3. Now, an easy mistake to make, and the mistake I made on my first take of this video, and the reason I'm shooting it again right now, is because I messed up, and see this 3 is downstairs, right? So what I did was when I pulled it out, I said, oh, I'm pulling out a 3, and I just put it right here. What's wrong with that picture? Well, that 3 was in the denominator, and I just put it upstairs, not in the bottom of a fraction. So instead of getting 1/3, the answer I got was 3. And luckily I caught what I had done very quickly, but very easy mistake for you to make, and I see students make it all the time. It's really challenging to factor stuff out of denominators and remember to make it a fraction. So I don't know how many tricks to help you remember to do that, other than just like, that's one of the biggies. That's one of the big algebraic mistakes students make all the time. All right, let's take another crack at a different sine one. Once again, this is really close to the theorem thing they gave us. It's just a little bit off. There's an extra 3 right here. Now this one I can't factor out. And I see students want to do this all the time, but you can't do this. You can't say, oh, sine 3 theta. Well, really, that's the same as 3 times the sine of theta. That's just not the way it works. This 3 and this theta are sort of like bound together inside, right behind the sine. There's no way to pull one out. That just is not legal, okay? So we cannot do that. So we don't have the option of turning this 3 theta into a theta, like we did in the previous problem. But what we could do is magically conjure a 3 to go here, because really what we need is for the 3 theta here to match whatever's down here. So if I have a 3 there I can't get rid of, I better figure out a way to put a 3 downstairs. The way I'm going to do that is I'm going to willy-nilly multiply this whole thing by 3/3. Now you do this in fractions all the time when you want to convert, the denominator to have the least common denominator or whatever. You multiply top and bottom by the same thing all the time, right? It's just something you're totally allowed to do, no big deal. So what this problem became is now is limit as theta approaches 0 of 3 sine 3 theta over 3 theta. Now you're starting to see what magic we just perpetrated here. So now I've got it perfect. This 3 theta right here represents what's down here. So this thing right here is exactly the rule. The sine of something divided by that same something, the limit is 1. I just have this extra 3 right here now, right? Because I wanted the 3 downstairs, but then I simultaneously had to put this 3 upstairs, which now is in the way. It's messing up my stuff. So what I'm going to do is I'm now going to take this 3 and put it out front. So what I've got now is 3 times the limit as theta approaches 0 of sine 3 theta over 3 theta. So this is sweet, right? This thing right here is exactly the rule, just the sine of something divided by that same something. So this all is equal to 1, but I've got a times 3 out front, so it's 3 times 1 is 3. Pretty crazy, right? The extra 3, in both these problems I just worked, we had an extra 3 in it, somewhere in the problem, and that ended up with an extra 3 appearing in the answer. In one case it showed up in the denominator, in the other case it showed up in the numerator, so we got 1/3 versus 3. That's what you have to be careful with, and that's why you can't just look at the problem and say, oh, I bet you put a 3 in there and just guess what the answer is. You really need to follow through the steps that I just did in order to make sure the 3 shows up in the right place, but that's what's going on. Alright, so turns out the same thing happens with cosine problems. So let's take a look at this one. Here we've got, now if you look at the cosine formula, it's got a 1 minus cosine of x over x. So once again, we need that x and the x to match. In this case, we're doing pretty good. We've got a y and a y. Those already match, so we're looking pretty good. The problem is we have 2 here and 2 here. That's annoying. We wish we had a 1 and a 1. But wait, couldn't we factor out the 2? So what I'm going to do is just turn this into, factor out a 2 from the numerator, so I'll get 2 times 1 minus cosine theta, or cosine y, I guess, over y. So now you can see right here I have exactly what I want since I pulled that 2 out. I just have an extra 2. But that's easy. All I do is scribble it out there, put it here instead, just move it outside. So now I've got 2 times the limit of all this stuff, which is 1. Oops, sorry, 0. Because the limit is 1 minus cosine x over x is 0. So all this stuff became 0. And now I've just got 2 times 0 is 0. Pretty exciting stuff. Alright, this next one is really similar to the previous one we did. I've got a 3 theta here. Can't get rid of the 3. There's no way to get that 3 out of there. So what I've got to do is concoct a 3 down here. So I'm going to multiply by 3 over 3 in order to have a 3, you know, to multiply by this theta guy. So now I've got a limit as theta approaches 0 of 3 times 1 minus cosine 3 theta all over 3 theta. But I just have, so now this looks perfect. This part looks perfect. I've got 1 minus cosine 3 theta over 3 theta. The 3 thetas match, so I'm all set there. I've just got to, you know, move this 3 out front. So I'll end up with 3 times, and then the limit of all this cosine junk is now just 0 because this exactly matches the theorem up here. All right, now see how those cosine ones are a little boring because they always equal 0? Perhaps we've noted a trend. I don't know. They are more likely to turn into 0, obviously. All right, so now we've got another set of stuff to look at. These ones are a little funkier because you notice we have x squared, we have squareds in here. Well, let's see what happens. So these are both indeterminate currently. So for example, this one right now, if I plugged in 0, I still get 0 over 0. It's indeterminate. But what I could do is say, you know what? Limit as x approaches 0. Sine squared x is really sine x times sine x. And of course I still have an x downstairs. Now the reason breaking up that sine squared into sine times sine was a good idea was because look at this. I've now got a sine x over x, which matches my theorem right here. I've got an extra sine x, which is annoying, but hey, that's not so bad because there's a theorem that says, hey, or there's a limit property where if I have a limit of something times something, I can break it up into two limits. So I'm just going to take the limit of sine x times the limit of sine x over x. The limit of sine x over x is just 1, right? Because that's just equal to 1. So the only thing that's left is my limit as x approaches 0 of sine x. So now I can just try to plug it in again. What happens if you plug in 0 to sine? Sine of 0 is just 0. Problem solved. Now you're probably thinking, hey, wait a minute, what did we accomplish? Because when we first plugged in originally, didn't we get 0? So why do we bother going through all this extra math? Well, no, originally we got 0 divided by 0, which is indeterminate. But now, after we did all that math and canceled stuff out, we just had the limit of sine x, not a fraction, just the limit of sine x. So this time when we got 0, it wasn't 0 divided by 0. It was just plain old 0, and plain old 0 is a fair answer to a limit question. Like, that's okay. All right, if you like that, you're going to love this one. Cosine squared. Now, in this previous one, I said, hey, you know what? Sine squared is sine times sine. And then cosine squared is cosine times cosine. The problem is that I've got this 1 to worry about and stuff, so it turns out the big trick on a problem like this is it's a difference of squares. So this is going to be the limit as theta approaches 0. I'm going to factor that 1 minus cosine squared into 1 plus cosine theta times 1 minus cosine theta. Oops, I guess these are 3 thetas. And then the 3 theta, I'm going to put under the 1 I want to match the rule. So 1 minus cosine x over x. So my 1 minus cosine 3 theta over 3 theta. So I'm just going to put that 3 theta with this guy. So this exactly matches. You notice how I have 3 theta, 3 theta? So that exactly matches this cosine rule. Which leaves me, all right, so you can see how by factoring this thing, which may not have looked like a difference of squares, except now that you've seen it, you realize, oh, that's a difference of squares. So now if you see it on your test, you may recognize that. But the point is, once you factor that to difference of squares, we magically had a little chunk of the problem that exactly matched this, which allowed us to just cross that out and replace it, which is really nice. All right, so here's a couple of nasty ones. What makes these nasty is that they're just using tricks we've looked at earlier, but like multiple tricks at the same time. So first thing we need to do is break that sine squared into sine times sine. So this will be the sine of 5x times the sine of 5x. And of course we'll tell this x downstairs and the limit. So right here is pretty close to working, right? But then we have to use the first trick I showed you, which is, because this 5x doesn't match x, we need a 5 down here to go with the 5 in front of this x. But of course, we can't just stick in a 5 anywhere we want to willy-nilly. We got to put a 5 in to compensate. So since we put a 5 in downstairs, we got to put in one upstairs as well. So 5 times sine of 5x. All right, so now this just becomes 1, because that's what that theorem says. So since that's just 1, we have the limit as x approaches 0 of 5 times sine of 5x. Of course, you plug in 0 to sine, you just get 0. So this is really just 0. Not too bad, though. At least it's not indeterminate, right? Maybe not. All right, next one. You can see the same thing's going to happen. That 1 minus cosine squared, once again, I'm going to factor to 1 plus cosine theta and 1 minus cosine theta. But of course, that 9, what is that 9 doing there? Kind of annoying, right? In this case, we actually can just ignore the 9. So instead of coming up with extra 9, we want the 1 minus cosine theta, and we want the theta to become a 0. That 9 we don't care about, so we just kind of fork it out of there. All right, so this becomes... All right, last couple ones. Just want to show you, one thing I can throw at you is making it upside down. So this thing right here looks pretty close to this, except it's upside down. But any fraction that's equal to 1, so basically, what this rule is saying is that the fraction sine x over x is equal to 1. But if a fraction is 1 this way, if you flip it, shouldn't it also be 1? All the fractions I can think of that are equal to 1, like 2 halves or 3/3, if you flip a 3 and a 3, you still got a 3 over 3. So that's what's going on here. Just because it's upside down doesn't change anything. It's still going to be what you thought it would be, but we still need the 2x to match. So since we have a 2x here, we need a 2 here. But that means we got to put one downstairs to compensate. So now all this stuff, limit of 2x over sine x is just 1. So we're just left with a 1/2. And like I said before, this 2 down here, we just got to be really careful to remember that, that's in the denominator, because it's compensating for a 2 we left upstairs. So that means when we pull it out and all we have left is that 2, it's got to still be in the denominator. So we get 1/2. Last one. This looks crazy. There are no rules for tangent, but tangents are just sines over cosines. So what we'll split this up to is a sine squared theta over cosine squared theta. And hey, we've also still got a theta squared downstairs, right? Now we're going to use our breaking up the exponents trick, where sine squared is really sine theta times sine theta. And theta squared is really theta times theta. And of course, we still have a cosine theta as well. Oops, cosine squared theta. So what's going on? Well, this sine theta over theta matches this. So that's just 1. We have another sine theta over theta, which is also equal to 1. And then what we're left with is just that cosine squared downstairs. So far we've gotten down to just limit as theta equals 0, theta approaches 0, of 1 over cosine squared theta. Now you might be thinking, hey, let's break up that cosine squared into a cosine times a cosine. But you don't actually have to do that, and there's no reason to do that because we can just plug in right now. If you plug in 0 for theta, cosine is equal to 1. And if you square 1, it's still 1. So we just get 1 over 1, which is 1. All right, so you can see how they can just throw multiple rules into a single problem. And that's ultimately what makes a hard class harder than an easy class, is whether they give you the easiest problems or they give you ones where it requires several steps. But either way, you want to get pretty comfortable with sort of mixing and matching and separating things and all this sort of algebra we're going to do in calculus. Because that's really why they teach you limits to begin with, I think, is they sort of want to set you up for being able to just do a lot of algebra and apply a lot of rules that you don't necessarily know what they mean or why we're doing it. And limits are, full of that situation. All right, so catch you next time.